Hello everybody, welcome to lecture 15 in MA 283 Linear Algebra. This is the first lecture of week 8. And today our goal is to talk about some subspaces that are related to the kernel and image of a linear transformation and to state and prove the famous Rank-Nullity Theorem, which is a really important and very frequently used theorem in linear algebra. So our setup is that we've got a linear transformation phi, or phi, which goes from V to W. It's a transformation of finite dimensional vector spaces. So V and W are finite dimensional vector spaces over the same field F. And so in that situation, we have a subset of V called the kernel of this transformation phi. And that's defined to be the set of elements of V whose image under the transformation phi is the zero vector of W. Okay, so the kernel of the transformation is the set of those elements of the domain that give us the zero vector in W when we apply the linear transformation to them. And that's a subset of the space phi. So we'll see shortly that not only is it a subset of V, but it's actually a vector subspace of V as well. And the dimension of that subspace is something that we're generally interested in because it captures an important feature of the linear transformation phi. Okay, so the kind of companion to that definition is the definition of the image of the function phi. So the image of phi, which I'll just denote by image of phi like this, is the subset of W consisting of the images under phi of all the elements of the domain V. So the image is what you would think it is. I mean, there's nothing special here about the fact that phi is a linear transformation. For any function, we can define its image as just a set of images of all elements of the domain under the function. So that's the image of phi. So the assertion is that the kernel and image of phi are subspaces of V and W. And of course, that means that if V and W are finite dimensional vector spaces, then this kernel and image of phi have dimensions, which are respectively at most equal to the dimension of V and the dimension of W. And so we have some kind of numbers attached to the linear transformation phi, which we can, in principle, do something with and work with. Okay, so just to quickly comment on why it is that the kernel of phi, for example, is a subspace of V, let's just recall how we can do that, or how we can show that from nothing but the machinery of linear transformation. So we have no special knowledge about what V is or what W is or what this transformation phi is, yet we can say that the kernel of phi is a subspace of V. So what we need to do to show that is to show that the kernel of phi is closed under the addition operation of V, and that it's closed also under multiplication by scalars in V. So to see this, we need to show two things. First of all, that the kernel of phi is closed under addition in V. And to do this, if we give ourselves a pair of elements in V, the kernel of phi, then we need to show that their sum in V is also in the kernel of phi. And to show that something is in the kernel of phi, you have to look at what happens to it when you apply phi to it. Okay, so because phi is a linear transformation, it respects addition in V, so that we know that the image of U plus V under phi is the same as the image of U plus the image of V. The image of U under phi is the zero element of W because U is in the kernel of phi. The image of V under phi is the zero element of W. So the image of U plus V is the zero element plus the zero element, which is the zero element. So certainly the conclusion there is that U plus V belongs to the kernel of phi whenever U and V separately do. And so the kernel of phi is closed under addition in the vector space V. Okay, so the second thing that we need to show is we need to show that the kernel of phi is closed under multiplication by scalars. So to see this, we have to give ourselves an element of the kernel of phi, let's call it little v, and we need to give ourselves a scalar. So give ourselves an element lambda of the field F, so lambda is a scalar. So we have to satisfy ourselves that if V is in the kernel of phi, then so also is any scalar multiple of V. And to satisfy ourselves with that, we have to apply phi to lambda V and hopefully get 0 in W, or hopefully show that we can get 0 in W using nothing but the definition and basic properties of linear transformations. Phi is a linear transformation, so that we know that phi respects multiplication by scalars. In other words, applying phi to a scalar multiple of v is the same as applying phi to v itself and then doing the multiplication by the scalar over in w. Phi of v is w because v is in the kernel of phi, and lambda times the zero vector in w is just the zero vector in w. And so the conclusion there is that lambda v belongs to the kernel of phi whenever v belongs to the kernel of phi and lambda is a scalar, so that the kernel of phi is closed under both addition and multiplication by scalars in v. So the same argument, or very similar argument, completely analogous argument, applies to show that the image of phi is a subspace, not only a subset of the vector space w. So I'll leave that one to you. Following the steps here should hopefully allow you to construct a similar argument for the image of phi. Okay, so like everything else in linear algebra, the kernel and image of a linear transformation have a matrix interpretation and an interpretation that depends only on matrices. So just to see how that works with an example, suppose we look at the linear transformation from R3 to R2, which is defined as left multiplication by this 2 by 3 matrix A. So this is a transformation that takes elements of R3 to R2, and what it does to them is just multiplies them on the left by the matrix A. That gives us, of course, a linear combination of the columns of A, which is a column vector with 2 entries, so it's an element of R2. Okay, so by definition of the kernel consists of all those vectors in R3 with the property that when you multiply them on the left by A, you get the zero vector. So the set of all columns in R3 with entries x, y, z, where x times the column 2, 1 plus y times the column 3 minus 2 plus z times the column 1, 1 is equal to 0, 0. So in the matrix context, the set of all such vectors x, y, z is referred to as the null space of the matrix A, or sometimes as the right null space of the matrix A. We can give an exact description of its elements by just applying a row reduction, because what we're looking at is a system of 2 linear equations with 3 variables, x, y, and z, and we can reduce its coefficient matrix or its augmented matrix to reduced row echelon form and give a description of exactly what the solutions of that system are. So in this particular example, there are 3 variables and 2 equations. So as expected, we get at least one free variable. We get exactly 1, and we get a one-dimensional null space consisting of all scalar multiples of the vector minus 5, 1, 7. So it's a one-dimensional subspace of R3, and we should expect that it should be a subspace of R3 because it's the kernel of a linear transformation. Just one remark about that actually while we're here. So we're saying that every vector of the form every vector which is a scalar multiple of minus 5, 1, 7 satisfies this equation with x, y, z equal to minus 5, 1, 7, or any scalar multiple of that vector. And of course, one of the ways of kind of thinking about what that means is we're saying that minus 5, 1, 7, with respect to the ordinary scalar product in R3, is orthogonal both to the row 2, 3, 1 and to the row 1, minus 2, 1. So when we're looking for elements of the right null space of a matrix, really we're looking for vectors, column vectors, which are orthogonal to all the rows of the matrix. So we do have that kind of geometric interpretation as well of what's going on. But the piece of terminology from this slide, which is important, is the concept of the null space of a matrix. Okay, so the null space and the column space of a matrix then are 2 related concepts. The null space of a matrix, or sometimes referred to as the right null space, which doesn't need to distinguish, is the set of all vectors which gives you 0 when you multiply them on the left by the matrix. So it's the kernel of the linear transformation defined as left multiplication by the matrix. The image of that linear transformation is, of course, the set of all vectors in R2 that you can get by taking linear combinations of the columns of A. So it's the linear span of the 3 columns of A, which is a subspace of R2. So in the matrix context, this is referred to as the column space of the matrix A. So for any matrix, its column space is the space of all linear combinations of its columns. So it's a subspace of the space whose dimension is the number of rows in the matrix, and it's just the linear span of the columns of the matrix. So in this particular example, the column space is all of R2, because we can observe, for example, that the first 2 columns in the matrix A here, or the first and third column, or the second and third, any pair of the 3 columns, is linearly independent. It is therefore a spanning set of R2, which only has dimension 2. And we can note that in this example, the kernel, or the null space, of that matrix A is a one-dimensional space consisting of all scalar multiples of this vector, minus 1, minus 5, 1, 7. So the kernel is a one-dimensional space, and the image is the columns, is the span of the three columns of A, which is R2, it's a two-dimensional space. And of course, we can observe that the 1, which is the dimension of the null space, and the 2, which is the dimension of the column space or image, add up to 3. And 3 is the dimension of the domain of A, which is the space of all column vectors of length 3. It's R3. So the fact that the dimension of the kernel and the dimension of the image add together to give us the dimension of the domain is not a coincidence, or it's not an accident of this example. It's a sort of manifestation of the so-called Rank-Nullity Theorem. So the next business of this lecture is to state and prove the Rank-Nullity Theorem, which applies in general to any situation where you've got a linear transformation between vector spaces, at least if they're finite dimensional, but has a particular interpretation for matrices in terms of the dimensions of the null space and the column space. Okay, so the Rank-Nullity Theorem, what it does, it relates the dimensions of the kernel, image, and domain of a linear transformation. So it's a theorem that applies to any linear transformation whose domain is a finite dimensional space. It doesn't really have a version for infinite dimensional spaces. So one remark is that the dimension of the image of a linear transformation is referred to as its rank. So if a linear transformation has an image of dimension 2, then that transformation has rank 2. The dimension of the kernel, it's sometimes referred to as the nullity. The term rank is much more frequently used than the term nullity, but you do come across the term nullity from time to time, but most frequently in the statement of this Rank-Nullity Theorem. Okay, so what the Rank-Nullity Theorem says is that if we have a linear transformation from a vector space V to a vector space W, and V and W are finite dimensional, actually we really only need V to be finite dimensional, and phi takes elements of V into elements of W, then what the theorem tells us is that the dimension of the kernel of phi, which is a subspace of V, plus the dimension of the image of phi, which is a subspace of W, the sum of those two things is the dimension of V. Okay, so that's what the Rank-Nullity Theorem says, and it's really it's a powerful theorem from which we get lots of mileage. Informally, what it says, and this is at least a way that I often think about it, which I find kind of useful, is that basically you have it, let's say that V has dimension 5, for example. Phi is a linear transformation that operates in the space of dimension 5, and it maps everything there into some space W, and the image of this 5-dimensional space is some subspace of W. So what we're saying really with the Rank-Nullity Theorem is that the full dimension 5 of V has to be somehow accounted for between the image of W and the kernel, which consists of the elements that sort of get killed off as you travel from V into W. So for a start, it's saying that the dimension of the image of W can be no greater than 5, which is plausible, because if we were to think about a basis of dimension 5, the basis of V of 5 elements, if V has dimension 5, then certainly the images of the 5 basis elements would have to be a spanning set for the image of W, the image of phi. So it's hard to see how the image of phi could have dimension exceeding the dimension of the domain V. On the other hand, if we had 5 basis elements for V, some of them could get killed off, or some combinations of them could, in the passage from V to W. So maybe the dimension of the image could be less than 5. If we'd have a spanning set with 5 elements consisting of the images of the 5 basis elements, but that might not be linearly independent. So basically what we're saying is, if it isn't linearly independent, then there must be a kernel which accounts for sort of the missing dimension. So basically, if V has dimension 5, then the image of phi could have dimension 5 here as a subspace of W. In that case, the kernel of phi would be trivial. It would consist only of the 0 vector and be a 0-dimensional space. Potentially, if V has dimension 5, the image of phi could have dimension 4. In that case, there would have to be a 1-dimensional kernel. If the image of phi has dimension 3 and V has dimension 5, there would have to be a 2-dimensional kernel to account for that part of the dimension of V that doesn't turn up in the image. So that's kind of informally how the Rank-Nullity Theorem sort of works, and it's kind of, it can be a useful way to think about it. We are going to prove this theorem, and we'll do it. The full details of the proof are not in these slides, but they are in the lecture notes, but we'll prove it now on paper in this lecture. Okay, so here's the statement that we would like to prove for our vector spaces V and W of finite dimension. So to prove the Rank-Nullity Theorem, which is basically, as I was just saying, that the full dimension of V must be somehow accounted for between the dimension of the image of phi here and the dimension of the kernel of phi. So just to give ourselves some, just for convenience, we're going to write n for the dimension of V and k for the dimension of the kernel of V. or of phi, excuse me, of phi, which is at most equal to n, since obviously any linearly independent subset of the kernel of phi must be linearly independent of v as well, so it certainly can't have dimension exceeding n. So we're going to give ourselves a basis v1 through vk for the kernel, and we're going to extend that to a basis of all of v. So remember that we can do that. We can extend a basis of a subspace of some space to a basis of the whole space. So we're going to extend it to a basis, which we'll call B, consisting of the elements v1 to vk of the kernel and the elements vk plus 1 through vn, which give us a spanning set for the rest of v. So this B is a basis for v. What we're trying to do is relate the dimensions of the kernel of phi and the image of phi to the dimension of v. So really we'd like to show somehow that the dimension of the image of phi is n minus k, which is the number of elements in that basis B that don't belong to the kernel of phi. Okay, so since B spans V, every element of the image of phi has the following form. It's phi applied to some linear combination of the elements of the basis B. So A1, V1 up to AN, VN, where the A's are scalars from the field F. Now, if we apply phi to A1, V1 plus AN, VN, that's the same as taking phi as a linear transformation. So this is phi of A1, V1, and so on, up to phi of AK, VK is in there somewhere. And in the end, we have phi of AN, VN. Phi of A1, V1 is A1 phi of V1, and V1 is in the kernel. So the first K of these are the results of applying phi to elements of the kernel. So these are all 0 in W. So basically, these elements, A1, V1 up to AK, VK, all of these first K are in the kernel of phi. So when we apply phi to them, we get the 0 element of W. So the image then of this linear combination of the elements of B under phi, well, it's just the elements that survive after we knock out all the ones that are in the kernel. So we had, so this is phi of AK plus 1, VK plus 1. Up to phi of AN, VN. And of course, we can write that if we want to as AK plus 1, phi, phi VK plus 1 up to AN phi VN, where these A's belong to the field F. They're scalars. So what we're saying here is that every element of the image of phi looks like this. Every element of the image of phi is a linear combination of the images of the basis elements vk plus 1 through vn under phi. Sorry for the bad quality picture there. Hopefully this is a bit better. You can maybe read it a bit better. Okay, so we're saying that the elements, images of vk plus 1 down to vn under phi, that these elements form a spanning set. A spanning set of the image of phi with n minus k elements in it. And we'd like to show that n minus k is indeed equal to the dimension of the image of phi, and which would mean we'd like to show that these n minus k elements are linearly independent. Okay, so in fact, the claim is that this is a basis of the space image of phi. And to show that, we have to show that it's linearly independent. And what we need for that is to take some linear combination of those elements that's equal to 0 and show that all the coefficients must be equal to 0. So let's suppose that we have some linear combination of these n minus k elements, and let's write it as ck plus 1 phi of vk plus 1 up to Cn phi of Vn. Suppose this is equal to 0 in the space W, which is good at practice when you're thinking about arguments like this to remind yourself from time to time, where are you? Where is this element? Is it in V or is it in W? So it should be in W because it's a linear combination of images of things under phi. Suppose this is the 0 element of W. Well, that would say that because phi is a linear transformation, that phi applied to ck plus 1 vk plus 1 plus ck plus 2 vk plus 2 up to Cn Vn is equal to 0 W. And now this element doesn't live in W, it lives in V. And that would be saying that ck plus 1, vk plus 1, up to Cn Vn belongs to the kernel of phi, because that's exactly what it means to be in the kernel of phi, that your image under phi is the 0 element of W. Okay, but this means that this element, ck plus 1, vk plus 1, this combination of vk plus 1 through Vn, belongs to the linear span of the elements V1 up to Vk, which were that part of the basis of V that involved the kernel of phi. Sorry, hopefully that picture might be a bit better. But this is impossible, or it's impossible unless this element is actually equal to the 0 element, since the set V1 to Vk, Vk plus 1 up to Vn is independent in V. That means that no non-trivial linear combination of the second lot can belong to the linear span of the first lot. So we must conclude that the coefficients ck plus 1 through Cn are all 0. Otherwise, we'd have a non-zero element of the span of Vk plus 1 through Vn that would be a linear combination of the elements V1 through Vk. So the conclusion there is that the set consisting of Vk plus 1 through Vn is a basis for the image of phi. It's got n minus k elements in it. So the conclusion must be that the dimension of the image of phi is n minus k, which is n minus the dimension of the kernel of phi, which is exactly what we wanted to know. Okay, so the details of this proof, I'm sorry for the bad quality of the camera here. The details of this proof are in the lecture notes, so and, the text is exactly the same, so hopefully it's legible there, if not here. So please do have a look at it when you have an opportunity. The most important thing about this theorem is the statement, and also I suppose the kind of intuitive understanding of it. That what it's saying is if we have a linear transformation that maps an n-dimensional space into something, if it has a kernel of dimension k, then the sort of remaining part of the n-dimensional space, which is n minus k, must turn up in the image. So the image and the kernel must have dimensions which add together to give us the dimension of the domain. Okay. Okay, so that's what we have right now for section 3.2. And so the key elements, I guess, the key ingredients of this lecture that you might take away from it. First thing to recall, I guess, the definition of a linear transformation. It's as a function that respects addition and scalar multiplication. To be aware that any matrix defines as left multiplication. An n by n matrix defines a linear combination from Fn to Fm, where the entries of the matrix are in the field F. Okay, to recognize that every linear transformation can be represented this way as long as we have a basis in mind. And then the two sort of new things from this lecture, some terminology, to recognize the terms kernel, image, null space, nullity, rank, and column space, which are a bunch of different words for the same thing. So bearing in mind, again, the kernel and the image are subspaces of the domain and target space that are associated to any linear transformation. The null space and column space are the corresponding concepts for matrices, where we think about the linear transformation as being left multiplication by a matrix, then the kernel and image are the null space and column space of the matrix. And we also have these words nullity and rank. So the rank of a matrix is the dimension of the column space. The rank of a linear transformation is the dimension of the image. And of course, those two concepts are really exactly the same. The nullity, which is a less encountered word, is sometimes used for the dimension of the kernel, although it's mostly used in the description of the Rank-Nullity Theorem. So final learning outcome for this one is to be able to recognize and interpret and describe and hopefully prove the Rank-Nullity Theorem. But of those, prove is kind of the least important. To be able to recognize it at work and apply it where appropriate, where possible, is really an important skill for a linear algebraist. Okay, that's it for lecture 15. Thank you very much, everybody.